All right, we got these exponential functions we're going to work on here. Let me give you the definition, okay? F of x is b to the x, okay? Where your variable is the exponent. The variable is the power, and your base is constant. But the base is greater than 0. It just can't be the number 1. So when I talk about exponential functions with people, initially, we talk about a couple of them. We really have two types. And these are the two types. The first type is called a growth exponential function, and the second type is called a decay. Now, you know it's growth because you actually pay attention to the base. My base here is 2. So if the base is greater than 1, well, then your exponential function is a growth function. If the base is between 0 and 1, so I have 0 less than b less than 1, this is going to be a decay exponential function. So there's two types. Remember, your base has to be positive. Base could not be 1. And so that actually gives you two situations. So I'll say this is a type 1 situation, and this is a type 2 situation. Now, typically, how they get you to kind of learn about these is to say the following. Like, let's look at the first example. We're going to let y be 2 to the x power, and then we're going to find corresponding values of x and y. Right, if I let x be 0, x be 1, and x be 2, then y is 2 to the 0. Remember, I use this as an input. 2 to the first power, and then 2 to the second power. So notice what happens here. What's 2 to the 0 power? If you guys took beginning algebra, isn't that what?
0.
1. 2 to the first power is 2. 2 squared is going to be what? 4. Is that true?
Yeah.
Okay. 2 squared is 4. Then I'm going to say, let's add -1 and -2 here. So get 2 to the minus first power is 1 over 2 to the first power. 2 to the minus second power is 1 over 4. So this is about 0.5. This is 0.25. Now we're looking at the curve y equals 2 to the x. So let's actually look at why we call this a call this a growth curve. So let me check something really quick here. All right, we do have this. Let me see if I could bring a let's bring in a graph. Okay? Well, let's bring a graph here. All right, I guess we'll have to use this one. Right here is fine. But let's go back. You got these points? Here's the points we're going to plot. Zero, 1, 1, 2, 2, 4, -1, 0.5, -2, 0.25. X coordinate, y coordinate, x coordinate, y coordinate. We're going to plot these points for the curve y equals 2 to the x. And again, the variable is the power x, called the exponent. These are exponential functions. So 0, 1, let's plot 0, 1. Let's go right here, 0, 1. X is 0, y is 1. That's right here. You guys okay with that? 0, 1? And then 1, 2 would be to the right 1 and then up 2 units. And then 2, 4 is to the right 2, 1, 2, and then up 1, 2, 3, 4 units. If I were to continue, if x is 3, do you guys know what y would be? What's 2 to the third? 2 to the third is what? That's 8. So if x were 3 now, 3 units, go up 1, 2, 3, 4, 5, 6, 7. There we go, somewhere over here. Okay? So let me look at the point. 0, 1 is here. Zero, 1, 1, 2. What do we say? 3. 1, 2, 3. Hold on. Here's 1, 2. Wait a minute. 2 and 4 right there. And here's 3 and 8. Okay. Now, so far, to point out to you something, my curve looks like what? It's getting what? It's getting bigger really fast. Is that right? Now, what happens when x is negative 1? Go over here. Let me have you guys look at this. When x is negative 1, over here, what's y? All right, isn't that 1/2? So it's actually one right in the middle there somewhere. So when x is negative 1, y is 1/2. When x is negative 2, it's even closer. And so if I were to plot these points here, aren't I getting closer and closer to the x-axis? But I never cross the x-axis. Now, this point 0, 1 is a point I go through for every exponential. It's kind of special. Now, I'm going to also say to you that I never cross the x-axis. This is known as a horizontal asymptote, meaning that there's an imaginary line here that we never cross. It happens to be on the x-axis. So this is the curve, by the way. Y equals 2 to the x, and we call it a growth curve because as x gets bigger, y gets really what? Big. And there's a lot of phenomena in nature that can be modeled by an exponential curve. Anytime you have like population growth, population grows. We can model this with an exponential function. Even, we're going to see later, decline, population decline can be modeled by an exponential function as well. It's not going to be the growth curve, it's going to be the decay curve. Money is supposed to grow. When you invest your money, it's supposed to do what? Grow, and grow exponentially. So as time gets bigger, your money is supposed to your investment is supposed to grow much big too. Anyway, this is your growth curve, and this always happens, by the way, I say always, when the base is what? Greater than or equal to 1. You will always have a growth curve. Now, this is growth. What about the reverse? Decay, right? Right here, decay. Well, what does our base have to satisfy in order to have a decay curve? It has to simply be between 0 and 1, meaning it's smaller than 1. So any base that's smaller than 1 is a decay curve. So let's take a look at this, decay curve. And the common example I use for decay is I use this function, 1/2 to the x power. And then again, we're going to let y be f of x. We're going to generate these points again. So we're going to do the same sort of table we did over here. So let's do that. Here's my x values. Here's my y values. X is 0. I want 1/2 to the 0. When x is 1, 1/2 to the 1. When x is 2, 1/2 squared. Okay? And then when x is negative 1, I get 1/2 to the negative 1. When x is negative 2, I'll get 1/2 to the negative 2. Maybe I'll do another like x is negative 3. That'll give me 1/2 to the negative 3 power. Let's find all the y values. Okay? So you guys okay with this? We're looking at a decay. The base here is smaller than 1. All right. What is any number to the 0 power? What is any number to the first power? Itself. So this is actually 1/2. What is 1/2 to the second power? It's 1/4, and that's going to be point what? 25. Right? Now, what's 1/2 to the negative first power? Let's do some algebra. Okay, 1/2. Isn't that 1 over 1/2? Which is 1 divided by 1/2, which is 1 times 2, which is what? This is 2. Okay, you guys okay with that? That's 2. Let's do some scratch work. What's 1/2 to the minus 2 power? It's 1 over 1/2 to the positive 2. 1 over 1/4. 1 divided by 1/4, better known as 1 times 4 over 1. This is what? 4. And then this is going to be 8. So, the points we're going to plot, let me get rid of all of my scratch work here. The points we're going to plot are going to look like this. X coordinate, Y coordinate. 0, 1, 1, 1/2, 2.25, -1, 2, -2, 4, -3, 8. These are the points I'm going to plot. Okay? So we're going to get out another graph here. Let's put it right here. I'm going to have to scroll this way. Let's see if I could get this to work. All photos. We're going to get a graph here. All right, that's pretty good. Okay, remember this curve is 1/2 to the x power. So let's plot our points. 0, 1. 0, 1 again is up here. I'm going to put the dot. 0, 1. And then what's the next point? When x is 1, y is 1/2. So that's going to be x is 1 to the right. This will be right here. Okay. What happens when x is now 2? Y is going to be 0.25, which is 1/4. Notice as x gets bigger, the value of y gets smaller. In other words, we're getting close to that x-axis, but we're never going to cross it. So you're seeing what we start to call the decay curve. Okay, so as x gets big, y gets closer and closer to the x-axis. What happens when x is -1? Y is +2. So my point is there. When x is -3, go to the left, go up now 8. 1, 2, 3, 4, 5, 6, 7, 8 over here. So as I go to the left with my x values, I get larger and larger. So let's sketch the curve here. It looks kind of like this. This is what we call exponential decay. And there's a lot of phenomena in nature that behaves this way. This is your decay curve. And again, as you look at the values of x getting bigger, the values of y get smaller. They're decaying to 0. Over here, as x gets bigger, exponential growth, your y value gets very big. So exponential growth. So what's the key? In summary, here's what you guys can do. What's the deal? If your base is bigger than 1, what do we say this is? Exponential growth. Good. If your base is smaller than 1, but positive, exponential decay. So on your homework, for example, they're going to ask you to do things. They're going to say, hey, can you graph some of these curves? And in some ways, it's simple. The first problem they want you to graph is y equals 3 to the x, but they give it to you as a function. So graph this function 3 to the x. Now it depends. We could do it 2 ways. Let me be more specific initially so you guys can kind of see what they want you to do. Maybe we'll go with that. Okay. You know what's going to happen when x is 0? Y is 1. When x is 1, y is 3. So we go up 1, 2, 3 right here. When x is 2, y is 9. So Okay. So let's see where 9 would be. X is 2. 1, 2, 3, 4, 5, 6, 7, 8, and 9. There you go. And then when x is -1, you're going to the left now. That'll be 1/3. So it would be 1/3, and then you're getting closer to the x-axis here. So what I'm going to say is, with this picture, hard to see, but your curve is starting to grow very what? Very fast. Okay. This is the curve y equals 3 to the x. So the bigger the base, the faster it grows. Exponential growth. B is greater than 1. So they want us to kind of graph that initially to get an idea about how to graph exponential functions. And they're very easy to graph. Notice there's not a lot of work to them. The next question we have to graph might be something that looks like this, 1/3 to the x power. Now, what do you guys know about this base? My base is what? My base is 1/3. Is that smaller than 1? So is this growth or is this decay? This is decay. So, initially, when you have to graph these, say bring out a graph. You can start off again with same sort of thing. We know it's going to decay. When x is 0, y is 1. So I can plot that point. Now when x is 1, y is 1/3. So the further away we go, the closer we get to the x-axis. So we're going to start to draw this decay curve. Goes on forever. Okay, it gets closer to the x-axis. Now, what happens on the left? Again, when x is -1, y is going to be 3. 1, 2, 3 up here. So the reverse is happening on the left. When x is -2, y is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what happens now here is we're actually having the opposite happen. And as you read this curve, from the left to right, again, you notice you have what we call the exponential decay. And that's because our base is less than 1. So we're going to have us start to graph some of these curves, decay and growth. I would simply say to you, in all honesty, what I'm okay with, unless it's something very technical we have to look at, is they want us to just sketch the graph. So if we looked at number 5 and how to sketch this graph, and you said, oh, look how this looks. They want us to sketch the graph of y equals 10 to the x-axis. What I'll say to you guys is, here's what you probably want to do. What's my base? 10. Good. So since my base is 10, is that bigger than 1? Is that growth or is that decay? Good. So if you had to sketch this curve, try to draw an x-axis. Okay. X-axis, y-axis. You always go through the point 0, 1 here. Okay, here's my point I go through. And then what do I have to do? Draw a growth curve. So to the right, if I'm growing pretty big. You okay with that? I'm going to grow exponential. Exponential growth is the fastest growth. And then to the left, I just get close to the what? The x-axis. Here's the function y equals 10 to the x power. Here's an exponential growth. Was that simple? That's kind of what you do.
So you're gonna have to be precise?
Well, no, I mean, at first they might want you to do a few of them to be precise to get some graph paper, but once you identify its growth, we're just going to sketch. This is a sketch. It's not very formal. Okay? So if they want you to sketch the curve, which they probably will, you know what it looks like. It's growth and decay. So 7, we have a trick question. Tell me. Here's my function for 7. Is this growth or is this decay? Is that a growth curve or is that a decay curve? This is I don't know. How do you know it's decay? Let's see. Yeah, let's see. Take a look. See this power, negative x? See that power? See this? Let's see what this really is. This function is really 3 to the negative 1 times x. Is that true? Because that's what negative x is, negative 1 times x. And then I'm going to say, if you recall from beginning algebra, properties of exponentials are back. So I want you guys to note this property for exponentials. Didn't we say any base to the nth power raised to the mth power, you keep the base and you multiply the powers? Well, that's what we're thinking of, but we're doing it kind of in reverse. And you guys know, what is any base to a negative power? Right here. It's 3 to the negative first power. You guys know what that is? This is 1 over 3 to the positive 1 power. So don't forget, this is in a parentheses with the variable x. So what I'm showing you is that this function really is 1/3 to the x power. So yeah, this is a growth or decay? Decay. This is decay. You say why? Because the base is 1/3 and it's smaller than 1. That's why it's decay. All right, you okay with that? Okay. If they want us to sketch, just sketch a good old decay curve. Good old decay. Right? You go through 0, 1 again, and x is 0, y is 1. So we're going to go through this point here. And draw a decay. What does decay look like? It's going down to the x-axis as x gets big, and you have the reverse happening to the left there. Okay? This is the curve y equals 1/3 to the x power, where you have what we call exponential decay. That's all you have to do is sketch that curve. Okay, you guys okay with that? Now, here's the deal. They're going to have us sketch this very special function, e to the x. Okay, now let me ask you this question. Is this growth or is this decay? It's growth? How do you guys know it's growth? Huh? Is this, no, it's not the exponent. The base tells you whether it's growth or decay. What's your base here? The base is e. All right, so I'm going to say my base here, b, is the value e. Does anybody happen to know the value of the letter e? What's e? See this letter? It's called the exponential number. The exponential number. Meaning the one and only exponential number. Do you guys happen to know the value of e? I'll give you a hint. E is irrational. What does that mean? It could be written as, it's written as a decimal that's non-terminating, goes on forever. And then there's no pattern to the decimals. Pi is another example of an irrational number, so is e. E is probably the second most popular example of error. Maybe not the second, maybe about third. Could be argued. You know what E is approximately, ladies and gentlemen? 2.718. So we're going to actually see this in the future really, really quick. Future is going to come up fast. So I'm going to say, for the moment, take my word for it. Then I'm going to show you in the future, okay? You okay with that? 2.718. That's my value for E. Okay. Point being, E is my base, and it's greater than 1. So we're going to draw a what? A growth curve for the exponential function. And so it's going to look like this. It's going to go through 0, 1 again, and it's going to grow really fast. To the left, it gets close to the x-axis. X and y. So let me try to be a better artist here.
Professor, how can we plug in the values?
What's that?
How can we plug in the values in E?
How do we plug in? Oh, it's a good question. Meaning, how do we get the outputs?
Yes.
Right. So let's say if you had to find f of 0, e to the 0 power. F of 1, e to the first power. F of 2, e to the second power. F of negative 1, e to the negative first power, which is 1 over e. Let's say f of negative 3, e to the negative 3 power, which is 1 over e cubed. Now, e, again, is a special number called the exponential number. E is approximately 2.718. So that number would be raised to a power. That's a base. I'm going to show you later today where this comes from. Okay, you guys are going to learn today about the number e. Very important number. Okay, pi is important, e is important, square root of 2 is important. Okay, these are all famous irrational numbers. So I'll show you where e comes from. E is a very fascinating number. And by the way, this function we're looking at is called the one and only exponential what? Function. And that's a famous function. This is found in nature and science, business. This is found everywhere. So we're going to talk about this function in detail. All right, we got the exponential function. All right. We got the graph though. This is the graph here of the exponential function. Y equals e to the x. Now we're going to see where this comes from. You guys okay with that? You guys are going to have a good time today. Huh? Sorry. Number 11. Let's see if we can trick you. Is this growth or is this decay? Is it growth or decay? How do you know it's decay? You're right. Let's see. Let's do the algebra. Negative 1 times x. Oh, properties of exponentials again. What is e to the negative 1 power? So this is 1 over e to the x power. So in other words, this is my base b. If e is about 2.7, which is about 3, then 1 over e is about 1/3, which is smaller than 1. So this base here, ladies and gentlemen, my base being 1 over e is smaller than 1. So you're right, it is going to be exponential decay. So all we got to do is sketch a decay curve. So let's sketch a standard decay curve, and it goes through 0, 1. Now let's try to sketch this. I'm not the best sketch. Here it looks pretty good. This is okay. This is the function 1 over e. And yes, this is a decay curve. So there's a lot of things in nature that grow and a lot of things in nature that decay. What do you think actually, what grows again? Okay, kind of, but we don't really, that's not the kind of growth we're talking about. But I guess growth, population grows, ladies and gentlemen. Population size grows. You guys know that? And it grows exponential. It also can decay. Bacteria grows. Anybody have that nice potato salad in summer that was been sitting all day in the sun? You guys know what I'm talking about? Has extra mayo and eggs. Right? You should have been there at noon. Of course, you get there at 4.
Mr. Judge.
Right? And the potato salad's been outside for a long time. Guess what's in that potato salad? Bacteria. And bacteria what? Grows. How does bacteria grow? See this model I'm showing you guys? Bacteria grows what? Exponentially. Yes. And then you go to the doctor, and the doctor gives you what? Antibiotics. What is that supposed to do? It's supposed to cause that population of bugs that it's in your system, bacteria, to what? Decay. Yes, decrease, decay. So a good example to think of growth and decay is to think of that potato salad that you ate and you shouldn't have, or that macaroni salad in the summertime. You got there late, it's been there all day, you eat it, you get sick. Go to the doctor, got to get antibiotics to make that population size of bacteria in your body decay to 0, get close to 0. Very common, okay? Another thing that happens, again, your money, when you invest, is supposed to what? Grow. So when you retire, you're supposed to what? Have some money to live on. You guys understand what I'm saying? That's the idea. What do you do when you retire? Have money and go have a good time. That's the whole idea of retirement, yes. What's your retirement plan? What's the retirement plan? No, it's not to eat Allenby's. You gonna have any money to travel? Okay.
Right?
I'll eat burritos for the rest of my life. That's the only thing I like is burritos. Okay? Here we go. Yeah, I know. Every time I'm supposed to... Yeah, I'm recording. We got you guys. Hey, the world has to know what happens at ELAC. You know what I mean? We can't hide anything. Let me show you how your money grows. You guys ready for this? Teaching ELAC students about money. Oh, they don't like money. Sorry. Let me tell you what everything here is. You see this symbol here, A subscript 0. That's what's known as your initial amount. The initial amount of money you what? Yeah, your initial investment, call it what you want. So it's some money you started off with. Okay? And then R is your annual interest rate. Okay? T, that's the time you forget about your money. You allow your money to what? Grow. Okay? So when you make your deposit, you're supposed to forget about it until you kind of retire, right? And hopefully that's a long time. So that's your T value. T is measured very often in years. Okay? Because you have an interest rate that's also measured as an annual interest rate. RT, we just have to talk about N now. N is an interesting letter in your model here. Okay? N is the number of interest payments in a what? In a year. A naught, R, N, and T. Okay? So I have a worksheet, number 13. Here's how much we're going to invest. Right? Number 13 says an investor invests $5,000 what? Dollars. How much you gonna invest? $5,000. That's how much money Aunt Betsy gave you for your birthday. All right, $5,000. We're gonna see how much $5,000 grows to.
That's why you need to start.
You could use $500 to start. You could use $50 to start. Okay. In this model, they're gonna give you an interest rate of 8.5%, which is 0.08 what? 5 as a decimal. And then we're going to say in this question, they're going to forget about the money for 20 years. So T here is 20. R, this is my A naught. They're going to forget about the money for 20 years. You guys okay with that? So here's what's going to happen now. In this question, let's stop and think about how interest is compounded. They first want us to compound our interest. Let me write it down this way. Let's talk about the details of how to compound. A little bit. We did learn it a little bit in 110. It's back, and it's back in a meaningful way. Okay, our interest is going to be compounded. I'm going to tell you guys what this means. If it's compounded annually, you get interest compounded annually. You know what that means? You get one interest payment in a year. So after a year, they go, here's your interest. That's compounding your interest annually. N is 1. We're leaving our money here for how many years? 20 years. So, after the first year, they go, here's your money. Then after the second year and your interest, they go, here's your what? New interest. Third year, here's your what? Interest, and so on. All right. What if they say compound interest semi-annually? You guys know what that means? Yes, you get 2 interest payments every year. So like every 6 months, they go, here's your interest. And then another 6 months, here's your interest. Okay, so they're giving you 2 interest payments if it's semi-annual in a year. Then we have quarterly. Now, how many interest payments in a year is that? And here will be 4. So every quarter they go, here's your interest. Here's your interest. You know what do you do with the interest? Do you guys know, by the way, since we're talking about interest? The interest stays. You forget about it. Your interest stays. You don't say, okay, you're paying me my interest, I take it, and I'm going to use it. No, you're planting money here. And you're going to leave your interest with them so that your money can grow even faster. You see what I'm saying? So they'll give you your interest payment every quarter, every 3 months, 4 payments in a year. Leave the money there so you have more money to plant and you're actually going to grow your money. Okay, you guys okay with that? That's the idea. And then finally, you could get interest, let's say, monthly. You get your interest every month. Now, and here is 12 monthly payments. All right, you guys okay with that? Yes.
Which one would you say is the best one?
That's what we're going to compute and find out together.
Oh, we're gonna do each one?
Yes, we're going to look at this, each one, because it's a good lesson. Because eventually we're going to try to look at what's called continuous interest, and that's going to be even funner or whatever. Fine. You ready to have some fun? Here we go. First case, let's look at our annual picture. Let's see which one's the best. The amount is A naught 1 plus R over N to the NT power. Now, the reason I said to you guys, get your calculators and get them out and blah, 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 because we're going to get to use them. What's your initial amount? 5,000. Good. Isn't that how much you got for Aunt Betsy for your birthday? Good. What's the interest rate? 0.085. What's N? If it's compounded annually, N is what? Is that 1? And Maybe I should put it, we should put it what? Should we change the color? Can you guys see it? Let's see. Let's see this. 5,000. And here is 1, and is 1. T is 20. My interest rate is 0.085. So, this is what it looks like. 5,000, 1 plus 0.085 over 1, and 1 times 20 if I plug in all the values. So I get 5,000, 1 plus 0.085 to the 20th power. So ladies and gentlemen, this is 5,000 times 1.085 to the 20th power. This is where your calculator comes in. Now your calculator knows order of operation, so it's going to do the exponent first like it's supposed to do. 5,000 times 1.085 raised to the 20th power. Do you know what I get? This is approximately 25,500 and what? $60. So that $5,000 grew about what? 5 times in 20 years. 25,560. Okay, you guys okay with this? Huh? Yeah, I know. Take a look at that. So what do you guys think? You're gonna put that money away now, 5,000, so that when you retire, you're gonna have what?
But there's factors in there.
25,000.
There can be factors like depreciation.
Well, what you're really saying is this. What's being questioned is this, really. The interest rate here, this is a model, a math model. It's not an unreasonable math model. Interest rate, let's go back to where the interest rate is. See this? Annual interest rate. Let me write this down. Here's my R value. What you're talking about, or what the assumption really is here, is that your interest rate of 8.5%, it's an average interest rate. So you might say one year it was 8.5, another it was 8, and another it was 9, and so on. It's thought of as being an average interest rate. You okay with that? Okay, you guys okay with this interest rate idea? It's an average interest rate. So if you had a constant average here of 8.5%, this is what you'd have in 20 years. Now, this is just how many years? This is 20 years. Let's say, for example, you happen to be 25, right? Anybody here 25 like me? All right. I'm not going to leave my money for 20 years because that would be retiring at 45. How long am I going to leave this money for? At least 40 years, maybe 47 or 45 years. You guys with me on that? So if I left it even longer, then this money would grow what? Even bigger. Is that true? So if I change my time value, I'm just going to put a note. I'm going to put this as a note. What if my time was actually 40 years? I doubled my time. I get 5,000 there times 1 plus. Sorry. Let's see what changes. My base still is the same. 1.085. And now what happens with time, it's not 1 times 20. It's 1 times what? 40. You're right. So if I plug this in my calculator, this is how much my $5,000 would be if I just threw it, left it alone for 40 years. You know what it is now? If I left it for 40 years, oh my God, that's 130,000. 665. You okay with that? So leaving 5, is that right? Let me double check. I'm not gonna. That's right. So if you leave $5,000 for 40 years at this particular interest rate, what are you going to have? $130,665. after 40 years. Okay, you with me on this? Well, you guys might sit there and say, you know what, Mr. Judge, this is not a lot. All right, I mean, a lot is relative. A lot to one person may be not enough for another, and a lot to one person may be too much, right? But let me give you the idea behind retirement. You remember, and we're going to see this. Remember how our interest is compounded, whether it's annual, semi-annual, and all this other stuff? Well, what happens, do you think, when you keep adding more interest along the way? This is going to get bigger. So let me talk a little bit about that first before we answer this not a lot question. Let's look at, not annual now, let's look at what? Semi-annual, before I really make this point. Here's my point for semi-annual. I have the same model. I have the same model. 1 plus r over n raised to the nt power. $5,000. What's the interest rate? 0.85, which is 8.5%. What is n? N is what? 2. Thank you. And let's say the time again is 20 years. Okay, let's go back to the original question, which is 20. 5,000. I now have 1 plus 0.085 over 2. 2 times 20 is 40. This is going to give me, I have to do this computation right in here. Okay? 1 plus 0.085 divided by 2. $1.0425. So I get 5,000 now. 1.0425 to the 40th power. What does this come out to? You guys know what you get now? 26,425 approximately dollars. So let's compare. 25,560. Let's go back here. 25,560 versus 26,425. What was better? Let's answer your question. Is it better to have the interest compounded annually or semi-annually? That's semi-annual. Is that true? Because it's more money. So let's think about this as planting dollars. You planted dollars, and 6 months later they gave you some interest. What did you guys do with that interest? You left it. You replanted that interest. So you have the money planted and the interest planted. Then 6 months later, you guys want to see the difference? You got 26,425 versus 25,560. Yes.
So right now we're doing it as far as 5,000.
Yeah.
At the end of the year, if we do it semi-annually, so you would multiply the 26,425 times 2.
No. Go back. The model now is not getting interest compounded once a year for 20 years. Your interest was given to you if it's compounded semi-annually. You now have this. You have 2 interest payments every year for 20 years. So they're giving you interest every 6 months.
But my question is, do they continue to deal with the 5,000, or it just builds off of whatever you have after?
No, this is based on the original 5,000. So you start with 5,000, 6 months later, they give you some interest. What happens after another 6 months? They give you some more interest. That's 1 year. Second year, you have your money plus your interest planted. And then 6 months, they give you your interest. So this is 2 interest payments every year for how many years in this question? 20 years. That's it, nothing more. Yes?
What's the difference between when you invest money and then you have your low, moderate, and high risk? Would that go in effect when it comes to retirement? Can you lose your money? After
Okay.
you gain your money?
What you're really saying what you're really referring to, in all honesty, goes back to this question here. Now, I'm not an investment expert, so don't ask me for investment advice. However, what you're really asking for is this interest rate right here, 8.5%. Now, just to let you guys know, we're dealing with a fundamental model of what's your money going to grow to. That's it. That is it. What will your money grow to? What is exponential growth based on these ideas? That is it, nothing more. But when you want to bring out, high risk, low risk, medium risk, you're really referring to this interest rate. That's all you're referring to. Because you can make some investments that have a high rate, some investments have a middle rate, some investments have a smaller rate. This is an average. So that's what you're talking about, spreading out your risk for various places. You can get a high return, possibly higher risk, though. Now, all that means is it's an average. 1 year it could be 10%. The next year it could be, 4%. And the following year it could be a negative 3%. That's an average rate. So it's how volatile that rate average will be. Some could be conservative. There'll probably be a smaller rate. However, it's more consistent. That's all you're talking about. It all comes down to this, the rate idea in some way. Okay? Because it's an average, assuming an average rate. That's all. So we're just trying to compute that. So let's kind of look at the next situation, quarterly. How many payments do you have when it's quarterly? What do you think is going to happen with the dollar amount? You think we're going to earn, does it make sense that we're going to earn maybe better money, more money, because we're planting money along the way 4 times now, not 2, not 1? So let's see what that becomes. Here's 5,000. And then my rate again was 0.085. Again, here is 4. And then what's my time now? 20. Is that true? 5,000. 1 plus 0.085 over 4. 4 times 20 is 80. We want to know what this base really is. So my base is going to be 1 plus 0.085 divided by 4. It's 1.02125 to the 80th power. And let's find out what that is. 5,000 times 1.02125 raised to the 80th power. You know what this gives us? $26,887 approximately. Let's compare. If we got our interest quarterly now, what happened to our money? Do we have more money? Yes, we did. And again, why is that? Because you're planting more seeds along the way, and that's a good deal. What do you guys think about that? You guys know what I'm saying? This is going to get even more interesting. Remember I said to you guys, because some of you guys tell me, hey, Mr. Judge, that's not a lot of money. That's not a lot of money. You invested $5,000, and after 20 years, it's about $26,000. After about 40 years, it's probably closer to 32,000, blah, 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 133,000. If you did 40 years. You with me on that? Okay, now that's 5,000. That's a big investment anyway. If you change your investment maybe to 500, doesn't matter. Here's my point. When you save for retirement, are you saving, you're putting the money away just once? No. You're putting away what? Not just once. Every month you're putting money what? Away. Is that true? So you're doing this for how many years? 40 years supposedly. So every month you might put 500. Here's 500 this month, 500 next month, and so on. You're doing that for 40 years. The point I'm making is you're planting money every month. And on top of that, there's interest given to you, which is more money, and you're doing this for 40 years. So by the time you retire, it's not 130,000 necessarily. By the time you retire, it should be probably what? $1 million, maybe $2 million. Who knows? Depends on those interest rates. So when you retire, you're not retiring with $26,000 like you got here quarterly. It's more closer to what? $1 million, $2 million. That's money that you use when you retire. So this is the idea of planting money, investing, so that when you retire after 40 years, you know how much you're going to have. Does that kind of make sense to you guys? You guys see what I'm saying? What do you guys think? Is that interesting? Let's see what happens in a monthly setting. How many payments do you get monthly? How many payments in a year? 12. Let's see what happens. $5,000, 0.085, and here is 12, 12, 20 there. Let's do the arithmetic. Okay, again, we're going to need to know what this base is. Is that right? Oops, sorry. Okay, 0.085 divided by 12 plus 1. So 0.085 by 12 plus 1. Let me double check. 0.085 divided by 12 plus 1. And then you get 1.007083 approximately. What's 12 times 20? 240. Let's get rid of this. Let's put a 240 power. Okay. Let's see what we get monthly. This is about $27,185. Boy, isn't that amazing? Look at this. Monthly, when you get your money given to you monthly for 20 years, your $5,000 grew to $27,185. Okay. So, what's the moral of the story so far? It's better to do, what's the best thing to do? Monthly so far over, we started with annual. Sorry, this is not annual, that's semi-annual. You got semi-annual, N is 2. Then we had what? Annual. Here's this annual. What is N? N is 1. N is 2. N is 4. N is 12. Boy, what do you guys think about this? The more you what? Get paid interest, the bigger the payment at the end. Is that true? The bigger the growth. Does that make sense? That's the idea. How about if I said to you, let's get our interest paid. Not every month. How about every day? Let's say N be what? 365. That would be daily. Isn't that amazing? Get your interest paid daily. How about if we got our interest every hour? In other words, 365 times 365 days. How many hours in a day? Ooh. That's interest paid every what? Hour. How about every minute?
Oh my god. And 60 minutes.
How about every second? Oh my god. 365 times 24 times 60 times 60. This is every second. Do you think our money would grow bigger if we got paid every second? Yeah, the bigger the end, the better. How about if we got paid continuously? What does continuous interest mean? It's better than every second. It's continuous. N gets arbitrarily what? Big. You with me on this? All right, let's do this. You guys are going to like this. You guys ready? Here we go. Here we go. Remember I said to you, Let's see what this means. A is A naught 1 plus R over N to the NT power. Isn't that our formula? All right, now we said what here? What do we say? Let's try this out here. There you go. I'm going to let X be N over R. Remember I said to you guys I'm going to show you where this exponential number comes from? Remember I said to you I'm going to show you this exponential number shows up in science and business and math. It's in nature. Remember, what's the value of the exponential number? It's about 2.718. Okay. Here's what I want to say to you guys. If x is n over r, I'm going to do some algebra. This means that n is actually x times r. If I multiply both sides by r, I can solve for n. And then I'm going to say to you guys that, you know what? Pay attention to this ratio here. This is 1 over x. Okay? So my formula becomes A is A naught 1 plus 1 over x. And here, what is n? We said n, see this n, is x times r. So I'm going to place my n with x times r. Here's my n right here. And replace you with what? X times r. And don't forget there's a t already out here. So here's what's going on. 1 plus 1 over x. I'm going to keep this, I'm going to use my powers here, my power rule. So I can keep this. 1 plus x, here's my x. My power is outside this parentheses here with RT. Okay? Now here's what's going to happen. Here's the question here. What is this 1 plus 1 over x, the x power, as my n gets big? This means gets big. Okay? Number of interest payments. Remember n was getting big? We said, what do you mean? N here was 365. 365 times 24. 364, 5 times 24 times 60. And so on. N is getting what? Big. You with me on this? This is what's going on. Now, here's what I'm going to say to you guys. Here's the key. What do we say here about what we let x be? Let's go back so you guys can see. Go back here. If this value n gets big, you see n is x times r. R is your interest rate. Okay? R is the interest rate. R is constant. This means that my value for x is getting big. So when n gets big, so does x. That's all we're saying. So we say, okay, n gets big, so does x. X gets big. Let's take a look at what this becomes. This is where I'm looking at right here. Okay, this is a classic demonstration. Let's kind of see what happens. I have x here, and I got 1 plus 1 over x to the x power. When x is 1, I get 1 plus 1 over 1 to the first power, which is really 2 to the first power. You guys okay with that? Just kind of let you guys know where this comes from. Now I'm going to let x be 10. 1 plus 1 over 10 to the 10th power. That's 1 point, what's 1/10? It's 1.1 to the 10th power. Let x be 100. 1 plus 1 over 100 to the 100th power is 1.01 to the 100th power. All right, let's let x be 1,000. 1 plus 1 over 1,000 to the 1,000th power is 1.001 to the 1,000th power. Let's do another one. 10,000. 1 plus 1 over 10,000 to the 10,000th power gives you 1.0001 10 thousandths. You guys see any pattern here, by the way? We keep adding zeros, and then that power gets bigger. Let's see what these numbers come out to. All right, let me see what some of these numbers come out to. Here we go. This is, by the way, the value 2. 1.1 to the 10th power. You know what that is? Let's see what we get. This is about 2.59374. Now let's see what this other value comes out to. 1.01 raised to the 100th power. This is about 2.704813. And then 1.001 raised to the 1,000th power is 2.716924. Boy, let's get this other power here. 1.0001 raised to the 10,000th power. You know what I get? 2.718146 approximately. Let's keep going a few. Let's see what happens. Now I'm going to let x be 100,000. 1 plus 1 over 100,000th raised to the 100,000 power. You know what that is? That's 1 point. Add 4 zeros. 1, 2, 3, 4 zeros, and then a 1. And then 100,000 power. Let's do 1,000,000. 1 plus 1 over 1,000,000 raised to the million power. You know what you really get? Again? How many? 1, 2, 3, 4. 1, 2, 3, 4. 5 zeros and a 1, and then 1 followed by 6 zeros. Let's see what we get. All right. 1 point. 1, 2, 3, 4 zeros, 1 raised to the 100,000. 1, 1, 2, 3, 4, 5. You know what you guys get here? You get here 2.718268. 2. What do you guys notice? Anybody notice anything interesting? Do you see any money? Do you see any numbers that are starting to be what? Repeating? Okay, let's try this next one. 1 point. 1, 2, 3, 5 zeros. 1, 2, 3, 4, 5 zeros. A 1 raised to the 1, 2, 3, 4, 5, 6 zeros. You know what you get here? 2.718285. The point I'm making is, what is starting to repeat? You guys know what's going to happen? What's repeating here?
271.
Okay. If we continue with this process here, of x getting what? Big. This is known, by the way, ladies and gentlemen, you're looking at what's called a limit process. This is the limit as x gets big of 1 plus 1 over x to the x power. You know what this comes out to be? This is, by the way, approximately, oops, sorry, I had it, got rid of it. This is first one thing. It's approximately 2.718281828. Does this kind of look a little familiar? See this 2.8 business? See this 2.8 business? So as you keep getting bigger, bigger, and bigger for your x value, you know what we actually call this number, by the way? This is so special. This is the number we know as e, the exponential number. So formally, we actually say that this isn't approximate. Your limit as x gets big, 1 plus 1 over x, the x power, is identically equal to e, which is approximately 2.718. And ladies and gentlemen, this number e replaces, let me put it here in purple. This here is E. This is E. So what you get now is a very special formula. A is A naught E to the RT, and this is when you have continuous growth. The growth is, again, what? Continuous, not every day, not every hour, every minute, every second, even better. This is what we call the continuous growth model. And this is where the number E comes from. It's about 2.718. Okay, you guys okay with that? Okay, let's figure this out again. Let's go with what we've been talking about. Okay, now that we know about continuous growth, this is our continuous growth model that I just derived for us. It's continuous. Now, our initial deposit again was $5,000. My interest rate is 0.085 at 20 years. So let's go back with the idea that the amount would be 5,000 e to the 0.85 times 20. So you guys can do this in your calculator. 0.085 times 20. It's 85% of 20. 5,000 e to the 1.7. Okay. And just to let you guys know what this grows to, approximately $27,370. So what I want to say to you guys about this is notice the following. Continuous interest. If your interest were to be paid continuously, if that were possible to pay you that way, well, notice, what was it when you got paid monthly? It's $27,185. $27,185. If you got paid continuously, it's $27,370. So there isn't much of a difference at all, it turns out. Only $200 after about 20 years. So if you could get paid continuously, which would be the best thing ever, you can't because physically they don't pay you interest continuously. The best you could probably do is monthly, and that would be the best thing you can get. So anyway, that's how money grows. That's one example. So on your homework, you're going to have some more. Case on your final, you'll probably have some. But this opens the door to number 17, which is going to be, in this case, a population decay problem. So I want to say that population can grow similarly. We have P naught E to the, they call it KT, but it's really RT. Same idea. Let's put R for now. Okay? Now, what's going to happen here is if it's growth, it works the same way. Okay? But P naught here, what do you think P naught should stand for? That's the initial, or P sub 0. That's the initial population at time t is 0. Okay? T is 0, initial population. R is the growth rate. And of course, what is T? T is time. And it's generally done in years, but it doesn't have to be. But fine. So this is when it's growth. And then I'll say to you, you have the second situation when it's decay. The only difference here would be the following. Now, let me go back for a quick second before I go to decay. the general picture of population growth for models looks like this. Okay? You don't have an x-axis, you'll have a t-axis, you have a p-axis, and this is my initial, this is when t is 0, my initial amount. So p of 0 is our p sub 0. This is the initial population. So you can start off with some initial population, and as time increases, of course, your population increases. So we're looking at this growth here, this curve. As t gets big, your population is getting bigger. That's growth. Now let's talk about the other thing, which is what? Decay. So we got some decay here. So for decay, you can have a population decay. Okay, population decay. Again, this is going to decay. P is P naught E to the minus RT. And again, a lot of books change that R to a K when it's population. P naught still initial population when time is 0. We're going to see how that works for us. Okay, t is 0. And we're going to have R is the decay rate, our decline rate. T is time. I want to point out the difference, though. What's the major difference? That sign right there is negative. So what the graph would look like here for a decay model, T and P. Of course, decay goes the other way. Here's a P naught. Okay? And I want to really be exact. The portion of the curve that's really here that's described for decay, just like for growth, it starts right here. You don't really have that left portion. So this is decay, and so your population is decreasing as time gets big. So these are the two models you'll handle with population growth, population decay. Same idea. P of 0 is P sub 0 here. Initial population. And your population is decaying. So a lot of things decay. Population does decay, especially when it's bacteria. So I have question number 15. Yeah, this is actually 15, not 17, so let's go back. Question 15 on your homework deals with the population growth. Oh, this is growth. Okay. No, we didn't even do. Well, no, I numbered it incorrectly. This is actually 15. 15 is the population growth. 17 is population decay. Population growth, 15. ELAC student population in 2000 was 15,000 students. So this is ELAC population growth. So in year 2000, okay, in year 2000, you know what happened? My population was, or is in 2000, 15,000 students. Okay, and then they say has grown at an average with an average rate of 4% per year. So growth 4% per year. So you guys know this is my R. I'll put it here. R is 4%. It's growth. And then here's a question. What is ELAC's population in 2012? So the question here is this: in 2012, what is P? So P is P naught E to the RT, where P naught is, what's my initial population? 15,000 e to the, what's this growth rate? 4% we write as 0.04, the decimal representation. And then I have this value called what? T. Well, this is what we got to figure out. Notice what they said to us. Here's the key. In year 2000, I had 15,000. We have 15,000 students. 12 years later, we have to find out the number of students. Is that true? Now, yeah, when T, at 2000, year 2000, we start the clock. This is when T is 0. In other words, P of 0 is that 15,000, and you may already have guessed that because when we plugged in the value here, we plugged in what? 15,000. So we start the clock in year 2000. This tells me that in year 2012, how many years went by? T is 12. Good. So replace this T with 12 here. And then finally, you're going to get a population here to be 15,000 e to the 0.04 times 12. P will be, well, what's 0.04 times 12? 0.28. 15,000. E to the 0.28. Hold on. 0.04 times 12 years. 0.48. I put 0.2. $24,241. That's approximate students. Okay, so in 12 years, ELAC went from 15,000 to 24,241 students, and that's assumed a 4% growth rate per year. Okay? I'm pretty sure. Let me see. 15,000 times E to the what power? 0.48 power. Yes, 24,241. Punch that in your calculator. This is what you what? Get. Okay, you guys okay with that? All right. This is population growth. This is how population grows. Now let's look at number 17. Let's see what 17 is. 17, you got population decay. All right. A decay. So automatically, P is P naught, E to the minus RT. I'm going to say to you guys, let's be a little more formal. Let's put a nice K, I guess. And I want to emphasize that this is decay, so this has to be negative. You okay with that? Decay has that negative there for E. So here's what they say in 17. Bacteria that experiences antibiotics declines at a rate of 6% per hour. So my rate, let's write this down. R is 6% per what? Per hour. And yes, that's 0.06. Okay. If 5,000 pesky bugs are present at noon. So at noon, how many bugs? P is what? 5,000 pesky bugs at noon. When the antibiotics are initially applied. So you got 5,000 bugs there. They apply antibiotics. How many pesky bugs are present at 10 p.m. the same day? So 10 p.m. we want to know. So let's say this. Why is this P of 0? Noon is where you start the clock at T is what? 0. Is that true? And then, so we're really saying that our P naught is actually 5,000. That's the initial population. So when I look at this model, I say, okay, P is P naught e to the minus 0.06 times time t. My rate is 0.06. That's the decay rate. I have how many pesky bugs? 5,000. And going from noon to 10 on the same day, what's my time like? 10 is 10. So this is a 10. So here's what we get. P, 5,000 e to the minus 0.06 times 10. P is 5,000 e to the minus 0.6 power. Is that true? Okay, punch that in your calculator. Let's see what we get. Okay, let me try it again. We get 2,744. So this particular antibiotic reduced our population from 5,000 to 2,744 in how many hours? In 10 hours. Okay, so let's do a note here. I'm just kind of wondering. Let's note. What about when T is 24? In other words, what about the next day? Right? So if you ever got sick, food poisoning, you took those antibiotics, I guess, and you want to know how you feel the next day. That's probably dependent upon how many pesky bugs are in your system. See what I mean? P is P naught e to the minus 0.6 t. There's our model. Initial population is 5,000. Now, what's my time value now? 24. Okay? 24 hours later. What is 0.6 of 24? 60% of 24 is 14.4. So let's see how many pesky bugs are present now. Wow, look at this. I'm going to write this down. This is 2.787 times 10 to the minus 3 power. Do you guys know what kind of notation this is? Anybody take the prerequisite course? This is scientific notation. You guys remember science? Let me write it down. Scientific notation. How does that work? Let's write this down. 2.787. You remember this 10 to the minus 3 power here? Remember that? That says move the decimal. See that decimal point? Move it. How many spaces to the left? 1, 2, 3 spaces to the left. What do you do with the blank spaces? Add zeros. Here's what I'm saying to you guys. Here's what I'm saying. You went from 5,000 pesky bugs at noon. 24 hours later, one day later, exactly one day after taking your antibiotics, what's the population of pesky bugs? It's practically what? 0. Question. Yeah. Oh, did I mess up? It's 06. Duh, I did mess up, sorry. Okay, 06. That's going to move our decimal. Looks like we're going to have some pesky bugs after all. Okay, 6% of 24. It's 1.44. Okay. Darn it! I thought we were gonna get rid of those bugs. Okay, let's see what we get. Thank you. I thought that was darn pretty good. One day later, we've got no pesky bugs in us.
You're distracted.
That's really, yeah, I am. I am. Negative 1.44. Oh, that's, you know, we still got some bugs in us. Pesky bugs. 1185. So the population decreased to about 1185. Maybe we're just feeling a lot better. Okay? So after one day of your antibiotics, we're feeling a lot better. The population went from 5,000 down to what? 1185. You okay with that? So I guess we have to spend some more time with that as antibiotics to get the bugs out of our system. But that's kind of what that makes you feel better, right? You know, that's why when you get sick, you take some of these antibiotics to actually decline the population of bacteria. That's how it works. Nice. Whew. Okay. And then, we got some interesting things here now. Let's talk about these. Exponential equations. That's what we're going to talk about next. Okay. There we go. Now, in order to work with these problems here, we have to review properties of exponents. So let's go back again and talk about it. You have 2 to the third power. What was the base again? 2. Good. So the number 3 here is the exponent, or your power. So 2 to the third power, by definition, if you recall from beginning algebra, was I have to repeat multiplication with the base 2. How many of these? 3 times. So I get 1, 2, 3 of those. So this is 2 to the third power, which is 4 times 2. Final answer is going to be your 8 here. So 2 to the third power is 8. We already know that. 3 is my base. 2 is the power. So 3 times 3 gives me 9. Okay, good. So we know 3 squared is the value 9. So we're going to review this. And then we're going to use this property that any base to the 0 power is the value what? 1. Is that true? So this is something we want to remember too. This is what we had in beginning algebra. Any base to the 0 power is 1. So 3 to the 0 power is what? Is 1 as well. So what would you get if I told you you had 10 to the 0 power? What value is that?
1.
That's also 1. So I know 10 to the 0 is 1 as well. Okay? Let's see. What if they gave you e, that number e we talked about the other day? What is e to the 0 power? That's also what? 1. Good. Any base to the 0 power is the value 1. Is that true? So let's see if you guys remember another property. What was b to the minus n power from beginning algebra? What's your base to the minus n power? 1 over b to the what? Positive n. Yes, we're going to have to remember this too. So for beginning algebra, we may have had things like 2 to the minus 3 power was 1 over 2 to the positive 3, which is 1 over, what's 2 to the positive 3 power? Well, 2 to the third power, isn't that 2 times 2 times 2?
1 over 8.
That's 1 over 8. Good. Okay, we're going to have to remember these properties. Okay, so this is another important property here to remember. Okay. Let's look at some more examples of that property. What if they gave you 5 to the minus 2 power? What's that? That 1 over,
25.
that's 1 over 5 squared, which will be 1 over 25, because isn't 5 squared written as 5 times 5? Is that true? So there we go. All right, let's do some more here. What if you had, for example, 3 to the minus 3 power? 1 over 3 to the third power. What's 3 to the third? 27. You're done. 4 to the minus 1 power. Let's see if you're awake. What is that? 1 over 4. Is that true? You guys remember these powers? Because there was another property that said any base to the first power is actually just the base. Here's another property that you had from beginning algebra. Okay, you okay with that? Let's try another one. What if they said what if they gave you here 2 to the minus 2 power? What do I write down? 1 over 2 squared, which is 1 over 4, because 2 squared is 4. And then, what about 5 to the minus 1 power? What is that going to be? 1 over 5 to the first power, or 1 over 5. Is that right? Let's see if you're awake. I'm going to throw you a curveball. 6 to the 0 power. 1. Good. 1/2 to the 0 power. Is that 1? Okay. How about if I gave you 2/3 to the 0 power? What's this? Is that 1 as well? Okay. What if I gave you what? How about 5 to the minus 3 power? What's this? 1 over 5 cubed, which is? What's 5 cubed? Good. Look at that. You guys remember these properties. A lot of times when we talk about this subject, students actually forget these properties, and that's not a good thing because this topic is very simple. It's just you have to remember the properties. Now, what about if I told you, let's look at properties of 10. What's 10 to the minus 2 power? Oh, with the number 10, all of a sudden, what happens? People forget. 1 over 10 squared, which is?
1 over 100.
Okay, good. All right.
Just kind of have
Okay. Good, okay. Anybody okay with these things?
yes.
So, I mean, there's a few properties I could talk about just so you guys also remember. You had another property, any base to a power times a base to the what? Another power. What did you guys do with these powers?
We add them.
You add them. That's true. That's good. Okay. So this is another situation. And then I get b to the n over b to the m is b to the n minus m. And this is a division property. But these are some properties of exponents that you guys had. So, like for example, you know, if you had 2 to the third power times 2 to the second power, you said, oh, I know, that's 2 to the 3 plus 2, or 2 to the 5th, the value is 32. Okay? And similarly, if you had 3 cubed over 3 to the 4th power, we said, oh, that's 3 to the 3 minus 4 power, 3 to the negative first power, and that's 1/3. So this is an illustration of some of these properties that you guys work with in the past.
You didn't open the exponential.
Okay. So I'm just reviewing some properties here. Do you guys remember another important property? How about this? A base raised to a power raised to another power. What do I do with those powers? Multiply. That's right. Okay. So here's my nice properties from algebra, if you guys recall. And something like this, an example here would be, 4 to the second power raised to the third power be 4 to what power? 6. That's 2 times 3. Now, go what's 4 times 4 times 4 times 4 times 4. How many of these? 1, 2, 3, 4, 5, what? 6. Anybody know what this is? What's 4 to the 6th power? Huh? So 4 to the 6th power is 4096, just so you guys know. Okay. All right. We've kind of done some review. So now I'm going to say to you guys, 4096? Okay. We've done some review. Now let's actually use properties of exponents. Number 19. You have 2 to the x power is going to be 8. And they're going to want us to solve for x. You okay with that? We're going to solve for x. And we're going to use properties of exponents to do so. Okay? So let me go back here and get some space. The question's going to be, really, when you solve these, exponential equations, okay, you say, why are these exponential equations? Because they're equations that involve what? Exponentials. Now, does anybody know, what does the power have to be?
3.
Anybody know? Is it 3? Well, some of you guys can guess, and you say, I already know, kind of by from trial and error. You can tell me, you know what, Mr. Judge, x is the value 3. And you say, why? Because 2 to the 3rd power is the value 8. So you actually solve for x, right? Okay, you guys okay with that? Now, not all of them are done that easily in general. You can't just always guess the value. So here's what's going to happen now. Okay? I'm going to say to you guys, take a look at this. You see that my base here is 2? Now, what you want to do here is write this 8 with powers of what? My base 2. Write the 8 as a power of that same base. Now, do you guys happen to know, how do I write 8 as an exponential that has the base 2? You say you write it as 2 to the what? 3rd power. You guys okay with that? So logically speaking, what to say to you is this, that if you notice, we have here equality. And the only way the left side equals the right side is we already know one thing. The bases are the same. That must be what? That my powers have to be what? The same. Is that true? And so you're right. We're going to say x here is 3. So that's the logic behind it. Okay? That the only way I can have 2 to the x equal 2 to the 3rd is if the value for x has to be the number 3. Pretty simple idea. What do you guys think? Well, let me formalize this. Right? Well, how do we formalize that? You guys want to formalize it? Yeah, it's fine. We're okay.
So, Professor, we
Yes.
bring to the value of base,
Say it again.
we bring to the value of a base.
Yeah, you write. What you want to do is this. You want to notice that 8 can be written as 2 to the 3rd power. Now, why is that so important? Because this base here was 2. So if they have the same base and different powers, that means your powers are the same. So b to the n equals b to the m. What that means is my powers are the same. N is the same as n. This is what I mean by formalizing it. When I said this, I said, if you have this, now I'll formalize it. If b to the n is b to the m, then n is the same as what? M. All right, so that's number what? 19. 21 looks like this. 5 to the x is 125. So if I want to use this property that we're talking about here, what do you guys notice? Can I write, see this base 5? Can I write 125 as an exponential that has 5 to some power? What do you guys think? What's the power? 3. Good job. Pretty simple. 5 to the x is 5 to the third, and that means x has to be 3. Okay? Is that true? Here's my 3. Here's my x. The power is 3. That's all we're saying. Pretty simple? Okay, notice it's just properties of exponentials. 23. 10 to the x is 100. What do we notice? Here's my base 10. Can I write 100 as an exponential that has base 10? What power do we use here? Is that 2? Okay. Now what does this mean? 10 to the x is 10 squared. What's the power? What's x? X has to be the value 2. Okay? Notice that there. Just to point it out to you. X is the number 2. Is that simple? All right. You guys okay with that over there? You guys, is that pretty simple? Okay. 25. Okay. Let's see what you get now. 2 to the x plus 1 is going to be what? That's going to be 8. What's your base here? Yeah, look at this. What's the base? 2. Can I write 8? 2 to a power? Can I write 8 as an exponential that has base 2? What's the power? It's power 3? Okay. What does this mean here? Let's write this down. It means 2 to the x plus first power is 2 to the what? Third power. You guys want to tell me what that means? What does that mean about my powers? Since the bases are the same, 2, my powers have to be what? Equal. Thank you. What that means is x plus 1 is the value what? 3. Okay, you okay with that? So the powers have to be the same. Can you guys solve this for x? Yeah. Subtract 1 from both sides. X is what? 2. See if you're awake. 4 to the minus x power is what? 16. You guys okay with this one? So let's take a closer look. My base here is 4. Can I write 16 here as 4 to a power?
Yes.
What's the power? 2. It's 2. Okay. Here's what I'm going to say. 4 to the minus x is 4 what? Squared. So far, so good? Okay. 4 base, 4 base. What does that mean about my powers? What does that mean? Negative x has to be what? 2. Look at that. If negative x is 2, what is x?
Negative 2?
You guys can do that. Is that true? Now, that's it. You're what?
Done.
You're done. I just want to point out to you something to say, you know, if x is negative 2, 4 to the minus 2, is that equal to 16? Right? Isn't minus minus plus? Is 4 squared equal to 16? Yes, it's a solution. So you solve this exponential equation. Okay. Anybody have any questions so far? Is that okay? Told you this stuff's easy. Okay. 29. It's not so bad. 3 to the x minus 2 power is 81. Okay. What's my base? 3. Is that true? Can I write 81 as an exponential that has that same base 3? What does the power have to be? If I were you, I'd start thinking about powers of 3. 3 to the first power is just 3. 3. What is 3 squared? Right? Look at generate powers of 3. 3 squared is what? 9. What's 3 cubed? 27. 3 to the fourth. 81. Ah. Look at that. If you gave up, because the magic number didn't pop into your head, right? All you have to do is generate what? The powers of 3 like we just did. So you don't want to just give up. You want to say, okay, if I generate these powers, I found that 3 to the fourth is 81. So what that says to me is 3 to the x minus 2 is 3 to the what? Fourth power. And more importantly, same base. What does that mean about the powers? X minus 2 is 4. So if x minus 2 is 4 now, can I solve that for x? Add 2 to both sides, and you get x to be what? Positive 6. This is an exponential equation. Okay? Number 31. Okay, this is only for the A students. Hmm? What's that?
We're almost done.
No. Okay. Only for the A students. Now, you might say to me, why would you say that? Because take a look, right? It's easy. Good. The base here is 3. Is that true? All right. Now, it's the same idea. Can I write, well, let's look at this. Can I write this 9 here as 3 to a power? What power? 2. Good. Stay with me. 3 to the x. 1 over 3 squared. You guys good with that? Now, put a little bit of that algebra knowledge together. What is 1 over 3 to the second power?
1 over 9.
It is 9. We know that already. But how am I going to use this idea again? B to the n. If b to the n is b to the m, then remember n is the same as m. How am I ever going to use this in this example?
3 to negative.
Good. This is 3 to the negative 2 power. Be careful here. This fraction of 1 over 3 squared can be described as 3 to the what? Minus 2 power. Is that true? You guys remember that? Weren't we working on those? Absolutely. Guess what? What does that mean then? Yeah, it means you're done because what do you want to notice? X is what? Negative 2. Don't we have the same base? We have the base 3. The base 3, this tells us that x is negative 2. And double check. Remember we said for a solution 3 to the negative 2 power better to be 1 over 9. That is 1 over 9. Okay? We plugged in x being negative 2 for my variable x, that exponent. Okay, so I just want to point out, anybody have any questions on this here? You guys okay with that? You sure? Okay. Is that easy still? Isn't that so easy? So you guys could do this. Let's look at the next one. 2 to the x power is 1 over what? 16. Okay? Now, the base here is 2. Is that right? Can I write 16 here as 2 to some power? Say yes. What's the power? Well, no, hold on. Is the power 4? Good. 2 to the x is 1 over 2 to the 4th power. Okay. What do we do? What is this? What is this part? What is this? Remember this? Uh-oh. How do I write this part here? 2 to the negative 4. Good. See, 2 to the x is 2 to the minus 4 power. I can now use that relationship. I can say x is negative 4. You are done. Okay.
What about this where you put 2 and then it's like 1 over 16?
What's that?
Unless we write it the way you want it.
Well, I'm going through every detail, every step here.
Okay.
And because some people really need that detail. Okay. It seems like, oh, you go through every yeah, some people need the detail, so you know, they appreciate every step like that. Anybody have any questions? You sure? You okay with that? Okay. 35. Okay. How would you handle this question? 6 to the x is 6. Six to the x is 6. What's my power here for the 6 on the right?
1.
There's a 1 there. Is that right? Okay, good job. So x is 1.
Is that it?
That's it. Isn't that it? X is what?
Someone said it's always been 5 over 5.
You okay with this? You guys over there, you're fine? Is that easy?
Is this one gonna be on the final?
We're gonna
Look at this. Everybody thinks math is so hard.
It's hard.
Let's see. 2x, let's see. Let's see. It just got a bit harder for you with this question. 2, darn it. This is what they gave me. I got to solve for x. And that's all they gave me. You should kind of be happy. You guys know why? On the right side, what's your power? If you don't see anything there, that's a 1. Same base again. Base is 2. What are your powers? X minus 4 is what? That's 1. Is that true? Okay. Add 4. And what do you get for x? X is 5. Look at that. Now, I mean, go back and double check. Let's see if this makes some sense to us, right? Because, you know, finding a solution, we're saying x is 5. So if I plug in 5 here for that x, don't I get 2 to the 5 minus 4 power is 2 to the first power? What's 5 minus 4? 2 to the first power. Is that 2 to the first power? Sure is. Solution. So you're solving what's called exponential equations. These are some very specific exponential equations, but You know, that's where you start. $39. 4 to the x power is 8. Now, maybe now we're getting into the problems that you have to be an A+ student for. So, pretty sneaky problem here. Okay, this one's a sneaky one. Now, what have we been doing? We've been saying, here's my base 4. And we've been saying to each other, okay, can I write 8 as an exponential that has the power, has the base 4?
No.
You're right. How do you know? Let's generate powers of 4. 4 to the first is 4. 4 squared is 16. And, oh, I got a problem. I can't do this. So every one that we just did, we were able to do with this idea. Now we can't. What do you think we do?
Can we write 4 to the power of x as 2 to the power
Yes. Yes. Let's note a few things. Yes. You're right. Let me summarize this. Here's the idea. The suggestion is, notice this, that I can write my 4 can be described as 2 to the second power. And 8 can be described as what? 2 to the what? To the third power. You okay with that? Let's note, isn't 2 to the first 2? 2 squared is 4. 2 cubed is 8. These are the numbers that we see there as bases. And so what that gives you now is here, we get this. 2 squared raised to the x power is 2 to the what? Third power. You guys okay with that? Remember, this number is 4. Oops, sorry. This number is 4, and this number is 8. So you have 4 to the x power is 8 there. Okay, I just want to point that out to you guys. Now, properties of exponents. We're almost there. What do I do with these two powers? Right? What do we do? Do we add them? Any A+ students in the room? Do we add them?
Oh, you
Multiply them. Good. You multiply them. This 2 to the third. Excuse me. Okay. Absorb that. Isn't that a property we just looked at earlier? Yeah. Now, take a look. Same base. What does that mean about my powers? 2x and 3 are equal. 2x equals 3. Can I solve this for x? Divide by 2. X is 3 what? Halves. Wow, look at that one. Okay. That's a nice one. Like that one. Okay. What do you guys think? Is that pretty good? That's pretty simple, right? 41. Let's see. Let's see what you guys think about this. 9 to the x power is 3. Now, you might say, you know, Mr. Judge, we've been looking at it this way. We've been looking at this 9, and if I start generating powers of 9, 9 to the first is 9. 9 squared is what? 81. Oh, I have a problem like I had before. Now, you may say, but I know a little bit of something. I know that if I generate what powers? 3. Good. 3 to the first is 3. 3 squared. Sorry, I skipped it. I wrote it backwards. What is 3 squared? 9. Wow, those are the numbers. So I'm going to replace my 9 with 3 squared, and I'm going to replace my 3 with 3. And it's really 3 to the first, but okay. All together, 3 squared raised to the x power is at 3 to the first now. Is that true? What do I do with the powers? Good, you multiply. 3 to the 2x is 3 to the first power. Is that true? Now, what's the deal? Same base. What does that mean about the powers? 2x equals 1, absolutely. So we write this down. 2x equals 1. Divide both sides by 2. What do you get for x? X is 1/2. Yeah. So we can notice again the solution, this idea here of what we're doing. That means 9 to the 1/2 power is the value 3, and then this is actually the square root of 9. You know. So the 1/2 power for a base, or it's the 1/2 power when you have any base, is really the square root. And you know, this is how you handle some of these more complicated problems. Okay, what do you guys think? Is that okay?
Yeah.
Not so bad, right? If you remember properties of exponents, this is actually pretty interesting. But if you don't remember your properties, then it becomes very what? Difficult, okay? Challenging, we should say. All right, let's take a look at this. 1,000 to the x power is 100. Aren't we in that same situation? If I started generating powers of 1,000, don't we have a problem again? You okay with that? All right. Here's what I'm going to say to you guys. Anybody notice anything about the numbers 1,000 and 100? What's so interesting about the numbers 1,000 and 100? What do you think, huh? What's that? Powers of what? 10. Good job. 10 to the first is what? 10. 10 to the second power is what? 100. 10 to the third power is what? You're right. So notice 1,000 can be replaced with 10 to the third. What about 100? 10 to the second power. Right? You guys good with that? Yeah. That means we have 10 to the third power raised to the x power is 10 to the second power. Okay, anybody have any questions on this step right here? Okay, what do you do with the powers there? 3 times x is 10 to the 3x is 10 to the what? Second power. All right, you okay with that? What does this mean about my powers? What does this mean? 3x is 2. So if 3x is 2, can I solve this for x? Divide by 3. What is x? What do you guys think? Is that okay? Okay, you having fun yet? No? Here we go. Okay. 16x equals 1. What do I do with this? Good job.
That's it, 0?
I don't know. You tell me.
Yeah.
Is that 0? The only way
And z equals 1. It's fine.
The only way a base to a power could be 1 is if the power is what? 0, yeah. Get this tattoo. I've been telling everybody in the world to get this tattoo.
God.
B to the 0 is what? 1. Okay, you guys okay with that one? How about if you got a sticker or a t-shirt and the t-shirt said, I am B to the 0.
1. I am 1.
I am number B to the 0.
Yeah.
Oh my God.
You wouldn't buy that t-shirt.
Yeah.
I'm going to make that t-shirt, but I'm not going to sell it to you because then I'll be in the school newspaper.
Oh my God, why not?
Okay. I am number what? B to the 0.
Take a picture.